Single-phase transformers, part 2 of 5. What we're going to cover in this presentation are the factors contributing to transformer losses. We're going to take a brief look at transformer nameplates, transformer polarity considerations, multi-winding transformers and their applications. We're going to look at paralleling transformers and some of the hazards associated with paralleled transformers. So our transformer is 100% efficient. We've said in the past that VA in equals VA out of a transformer, but I think we can all appreciate that nothing is 100% efficient. So although small, there are losses inside a transformer, and for loading purposes, they are considered negligible and largely ignored, but they still exist, and we still need to have a basic understanding of how they affect the operation, and we'll look at them in further detail in a later presentation. So very basically, transformer efficiency is made up of the input, subtracting the losses, which are part of the transformer, equaling the output. And although the losses are very small in a transformer, they still exist. So what are these losses made up from? Well, there's kind of two broad categories. The first category would be copper losses, and the copper losses is down here. Copper losses are I squared R losses, and they are losses that we see because of the copper conductor that is used to wind, make the winding of the transformers. So when we push current through it, there's going to be heat generated. The other category of loss we see has to do with magnetic or core losses. And these are made up of hysteresis, eddy currents, and leakage flux. So let's look at each one. Hysteresis. Hysteresis has to do with the movement of these magnetic domains as they are aligned in 180-degree differing direction 60 times a second due to 60 hertz. And because of that, you would get a significant amount of heat being generated, and it's difficult to completely get rid of them. And so what we typically do is we make the core of a transformer out of silicone steel, because silicone steel is going to offer a little bit of lubrication and reduce the resistance of the molecular movement. The second one is called eddy currents, and those are circulating currents inside a solid core due to magnetic lines of flux. And when we get the circulating current inside the core, it causes heat to be produced. Now, what we do to prevent this is we slice the core up into very thin sheets, and then we laminate every sheet so there is no electrical connection between each sheet of the magnetic core. And we see that in transformers and motors and pretty much anything that utilizes electrical magnetic lines of flux in order to function. Last one is leakage flux, and that simply means that there is a little bit of flux that is not going to break across the secondary winding, and because of that, it is not considered to be useful. So there's always a little bit of leakage flux. It always exists. You cannot completely eliminate it, and that leads to a little bit of inefficiency in the transformer as well. So overall, what we get is two formulas that can be used to illustrate efficiency. Power input is equal to power output plus the losses, and percent efficiency is equal to the output divided by the input, right? Output plus losses times 100. So that equation doesn't change through any of your electrical training. Could be for a basic circuit, could be for a motor, or it could be for a transformer. Here's a typical transformer nameplate. What sort of information is useful on it? Oh, there's all sorts of different data. Some is really obvious and useful, and others we don't really use as much. So voltage, high voltage winding, low voltage winding, obviously that's pretty important. If it's single phase or three phase, what the frequency is. Maybe there's taps, and we'll look at taps in a later presentation. What do those do? What do they add to it? In addition, there's also VA. What's the total capacity of the transformer? What's the percent IZ? It's used to calculate the transformer's secondary short circuit fault current, and we'll do that in later presentations. What about the liquid? If it's a liquid-filled transformer, we need to know what type of liquid it is and also how many gallons are there inside, because that will make a difference in how it's installed and where it can be placed. So there's all sorts of information, and some of it's more useful than others depending on what the installation type is. Here's a typical transformer nameplate. It tells us here it's a 500 kVA transformer, so pretty large. Primary voltage is 4160, secondary is 480. It tells us that it has a percent impedance of 4.74%. Approximate weight, it's actually probably one of the more important items, almost 3,000 pounds. And here are the taps. And so we'll look at those in a later presentation as to why they are being used. This is generally what you would see inside a transformer. We've got lugs that are coming down, and those bus bars are connected to lugs, and the lugs are then connected to the transformer winding. And so the winding is usually they've got a enveloping type of winding. You see in the back there, there's the primary winding is the large one that we can actually see. The secondary winding is actually in behind. So it's kind of an interesting application. And then the markings or the identification of each of the terminals is alphanumeric. And we're going to take a look at what that signifies. We've got H's and X's, and we got numbers 1 through 3, including 0. So transformer polarity is what those markings are going to relate to. Transformer polarity is important when we take two or more transformers or windings and connect them in parallel. It's also important when one transformer is connected into an auto formation. And it's also important when instrument transformers are connected to their measuring devices. So what is transformer polarity? Well, the polarity has to do with the direction of current flow on a winding within a transformer. And it means that at any given point, we should be able to assign a polarity to either end of a component. So if current is traveling this way through a coil, or any other type of item within the electrical industry, it could be a resistor here, the point at which the current enters that device is going to be more negative to where it leaves. And if the winding is made opposite to the winding on the primary, see how the winding is opposite here? It goes in the opposite direction. It's going to cause current to flow in the complete opposite direction. So kind of an interesting application, and that's because of Lenz's law. So that means that the polarity, if we were to take a snapshot of the circuit, would be negative and negative at the same time here, and positive at the same time there. Now, this is important for some applications, and the markings are going to have to somehow account for this when we go and look at the terminals on a transformer. So, first off, these alphanumeric terminal identifiers will indicate where the high and the low voltage coils connections are located. So the high voltage terminals are always labeled with an H, and the low voltage are always indicated with an X. Now the numbers attached with the letters indicate which two terminals will have the same polarity at any given time. So H1 and X1, those two would have the same polarity during a snapshot of the circuit, and H2 and X2 would have a snapshot of same polarity at any time during the circuit's operation. Now, depending on their size and the voltage, transformers will be constructed by the manufacturer in one of two different forms. We actually have two different arrangements. One is called subtractive polarity, and the other is referred to as additive polarity. And this is an intentional difference in construction by the manufacturer to provide the terminals in a different location, but more importantly, they have been wound in a different way. On a subtractive wound transformer, you'll notice we have H1 and X1, both on the same side. And although just visually it looks a little different, there is a reason for doing this. So on a subtractive transformer, subtractive polarity transformer, it means that, again, same as what we looked at before, H1 and X1 will have the same polarity at any given moment, and H2 and X2 will have the same polarity at any given moment. On an additive polarity transformer, it's the one that we looked at previously. They are kitty-corner to one another, and the difference has to do with lifespan. How long will a high voltage transformer last for if wound subtractive or wound additive? So they wind them in different ways, and we don't need to focus on that significantly, but what's most important is that there is a difference in how they manufacture the transformer. And what also is important is that it has absolutely no effect on the transformer's operation or its capacity. So why then do we do it? Well, manufacturers, when they started making transformers, when they started making high voltage transformers, they discovered that in high voltage environments, like when we're talking 14,000 volts and 750,000 volts, there was a significant amount of voltage stress on the windings. And that massive voltage stress actually led to a shortened lifespan from what it was actually predicted to be. So it should have lasted longer, but this voltage stress destroyed the insulation on the windings and caused shorts and cracks, and eventually the equipment failed. So what they did is they discovered that by winding a transformer in subtractive polarity, the voltage stress was reduced. You don't need to follow through these calculations, but realistically, what I want you to focus on is this. A subtractive polarity transformer only has about 8,900 volts worth of stress across this gap between the two windings. 25,000 volt primary, 7,200 volt secondary. And an additive polarity transformer, that difference or that the stress between the two is 16,000 volts. It's almost double what a subtractive polarity is. And what that means is that when they make a high voltage transformer, they wind it subtractive so that it lasts longer because the voltage stress is lower. So generally speaking, this is an excerpt from an IEEE white paper, and it's just simply showing generally what you would expect to see in high voltage transformers, usually liquid filled. So if you were to exceed 8,600 volts, usually it's subtractive wound. If you were to exceed 200,000 200 kVA or 200,000 VA, you would also get into subtractive wound transformers. Instrument transformers used with utility energy metering indicate polarity with a white dot, and the dot location represents identical polarity at any given time. So there's a dot and a dot, dot and a dot. And on the real equipment, you'll see it like this. There's a white dot that's actually on the case and on the bus bar as well. Or if we're dealing with something like this is another instrument transformer. It'll actually indicate that by telling you which side should the CT or the instrument transformer face in regards to the source or the load. So there's an arrow here. It even says the word source on the front because that would make a difference to the polarity depending on which way you laid the conductor inside that CT. So something interesting to consider when you're out in the field. If a transformer has no numeric terminal markings, a polarity test can be done to determine if the unit is additive or subtractive wound. Now, the polarity test is going to determine the type of transformer construction by observing the outcome of voltage sources in series. So here is two batteries, 100 volts, 15 volts, put a jumper between them, and we know that sources connected in series, if they have alternating polarities, right, the positive to the negative side, they will add together, giving me 115 volts DC. If, however, I take one of those sources and I flip it around so that both of those positives are connected together, we will actually get a subtraction of voltages. So 100 minus 15, and it'll give me 85 volts. So if we did a polarity test with a transformer and we measured 168 volts from this open terminal to the terminal connected back to the source, remember we got a jumper in there, same as with our two batteries, and we have connected the rated voltage primary to that transformer. If I get 120 plus 48 equal 168, that means that we have an additive wound transformer. And we would know that the terminals should be identified as such. It's always going to be diagonal from the H1 is where X1 is located for a additive wound transformer. If we took the same test on a different transformer, and instead what we measured was 72 volts AC, this would tell us that we are dealing with a subtractive wound transformer, and that the terminal locations H1 and X1 are actually parallel to one another. Here. Let's transition now and talk about some multi-winding transformers. We have a few different examples on the front here. It's a control transformer. You can see from its little nameplate that we have 2 windings on the primary and 1 secondary winding. And then this is called a buck boost transformer, and it has 2 primary windings and 2 secondary windings. So, as we've observed, there's more than 1 winding on the primary and or the secondary. Important to realize that the primary windings are always identical in voltage, and the secondary windings are identical in voltage. So it's not like we're going to have 2 different voltage values. So let's take a look at the ratings. On a typical multi-winding buck boost transformer, what we're going to get is kVA rating, 2 voltages with a slash, and then we've got our semicolon here, which indicates the difference between primary and secondary, and another 2 voltages. So let's see what each one of these is going to relate to. Now, obviously, the kVA is the capacity of the entire transformer when all of the windings are used. On this other side here, we then have 2 voltages on the primary and 2 voltages on the secondary. The first voltage is going to indicate the voltage of one single winding on the primary. So 120. Each of them is rated 120. On the secondary, the first voltage shown is 240. So that means that each of the windings is rated 240 volts. Now what's with that second voltage? Well, the second voltage is there to show you what value of source you would need on the primary and what voltage of load you could supply on the secondary if you were connecting the windings in series. What if we connected the windings in series and we connected a source between H4 and H1? We would require a 240 volt source. What if we connected a load between X4 and X1 and we connected these two in series? We would then be supplying a 480 volt load. Important to realize also that each winding in this transformer is rated for half of the total transformer VA. And that's because, remember, the VA, the total VA is applied to the primary, 10,000 VA. And if there's 2 windings, it's divided equally, 5 and 5. Same with the secondary, 10,000 VA divided equally is 5 and 5. So let's take a look at calculating the individual winding current ratings. How many amps can each one of these windings carry? So again, we've got our VA divided by voltage, and we're going to do one single primary winding. And one single primary winding then means that we're taking the VA of one winding and the voltage of one winding. So 5,000 divided by 120 gives me 41.66 amps. Now remember, they're both identical in value. So that means that both those windings would have exactly the same current rating, 41.66 amps. We can do the same thing with the secondary. The secondary, each one of those windings was rated 240 volts and 5 kVA, which meant that if we take the VA of 5,000 divided by 240, we end up with 20.83 amps. And so again, the individual current ratings of each of those windings would be 20.83 amps. So the reason that manufacturers have chosen to build these is so that a single transformer could be used for many different source or load voltage applications. And so that means that they could sell the transformer on the right to 4 different people with 4 different source and load arrangements. But the transformer on the left, they can only sell to one person who wants a transformer to supply a 240 volt load from a 120 volt source. And as the caption at the bottom states, the reason that we can get these different orientations is because we're going to connect the windings in either series or parallel. So let's see how that's done. Parallel connection. Let's look at the source or the primary side. A parallel connection, and remember, each one of those windings is a source. So to connect them in parallel, we have to ensure that the polarity is consistent, right? Think of them as two batteries. So that means that the odd number terminals must connect together and the even number terminals must connect together. And then we send a wire out, single out from each of those parallel connections. It would have a 120-volt source, applying 120 to this coil and 120 to this coil. If instead we were to connect them in series, we're connecting 3 and 2 together, and we're taking the source off H1 and H4, which means we have double the value of source voltage required in order to drive this transformer. So we'd have 120 applied to each of these coils because 240 divided by 2 equally is 120. Multi-coil transformers are manufactured in this way so that we can do all sorts of different combinations. So not only can we do series and parallel on the primary, we can also do series and parallel on the secondary. So look at these 4 different connections. 120 source to 480 volt load, 240 volt source, 240 volt load, 120 volt source, 240 volt load, and 240 volt source and 480 volt load. You have 4 possible different connections, and that offers a significant increase in usability and also a reduction in cost because the manufacturer has now only made 1 transformer for 4 different customers. Now let's take these values that we calculated and actually apply them to the diagrams and see how many amps would I actually measure at full load. What is it capable of delivering for the primary and the secondary circuits? So let's look at the primary first, and let's look at a series connection because that's typically easiest. So for a series connection on the primary, whatever current flows through the first coil also flows through the second coil. So the current here is equal to the current there, which means H1 and H4 should be equal. And don't we already know what the current rating is of a single coil? I think it's 41.6 amps. So that means for the series connection, 41.6 amps would be measured there and would flow through both of these, right? Out in on H4, out on H1. What about the parallel connection? Would the individual current ratings change of each of those 120 volt coils? No, of course it wouldn't. What's going to change is the total amount of current that we would measure up here. So remember, each coil is rated 41.6 amps, and if I connect sources in parallel, what does that mean? It means that the voltage remains the same, but the current is going to add together. So that means 41.66 times 2 gives me 83.32 amps. So we'd have 83 amps. At full load, we'd have 83 amps flowing on these 2 conductors here for the parallel connection. The same thing can be done for the series, or sorry, for the secondary. Let's look at the series connection for the secondary first. There's the series connection, 480 volt, and we already know what the current value is for one individual coil, or winding rather, on the secondary. It's 20.83 amps. So 20.83, remember they're in series, so that means that for the series connection, the secondary current or the secondary load would be 20.83 amps. So the maximum load that you could connect to this orientation would be 20.83 amp 480 volt load. For the parallel, same application as what we did on the primary, we're going to take that 20.83 amps, and since there are 2 sources connected in parallel, we're going to double that current because the current from the first coil is going to come up to X3. It's going to travel over to X1, combine with the current that went through this coil, and they're going to then have a sum, which is 20.83 times 2, giving me 41.66 amps. So you can see it's a pretty easy application to calculate these values of current based on a multi-winding transformer if I know already what the individual winding currents are, right? And then we can work out what amount of load and what amount of primary current I would expect. So where are we going to use these multi-coil transformer applications? Well, there's obviously buck-boost transformers, which is what we've done a few calculations with. There's actually more combinations than what we just looked at, those four, and that would require us connecting them in auto formation. We'll look at those in an upcoming presentation. There's also high voltage utility service connections. And again, the purpose in multi-winding is that we can then connect this to two different voltages of source. They can either connect this transformer to a 4800 volt bus or a 2400 volt bus and still get 120, 240 out at the bottom. Let's look at that connection. It's a multi-winding on the secondary, and they have connected the two windings in series together, X2, X3, and a center tap connection coming off. By doing a center tap connection, there is a common connection to this side and this side, and that means that we have now just generated a neutral conductor. So this would be a single phase 120, 240 volt connection. What about control transformers? This control transformer is rated 24 volts. It has two primary windings, and it even has a tiny, if you really focus, you can see the difference in the connections, and I've just blown it up here with an illustration, but you can see metal links. There's the metal link or a bar that is used to connect the windings in either series or parallel. So that's in parallel, this is in series. So I have the application for this transformer of two different sources, depending on what voltage is available with the equipment that I'm using. Let's take a look at sizing loads to transformers. So load VA cannot exceed the transformer VA rating. That should be fairly obvious because the VA rating is the capacity of the transformer. So if we had a 240 volt load and 50 amps, single phase, what size transformer would require? Minimum would be 12,000 VA. Now, do they make a 12,000 VA transformer? At that point, you'd have to refer to the manufacturer's catalog of possible sizes, and we've got a little excerpt here from one of the main brands, and they have standard sizes that are produced for single phase and standard sizes for three phase. So if we had a 12,000 VA load, we are in between a 10 and a 15, and so obviously we'd have to choose the 15 kVA transformer. Now notice that the standard sizes are not the same for three phase as they are for single phase. And with three phase, they start at 3 and go all the way up to 3,000, whereas on single phase, they start at 500 VA or 0.5 kVA and go up to 333. So it really depends on what application you have. Sometimes a load is so large, it exceeds the VA rating of a single transformer. And in that situation, what we have to do is connect multiple transformers together in parallel to supply the load. And so a lot of times this is done where there is a very large load, like perhaps on a large building, or even on a grid system when we're talking utility distribution, where we need multiple transformers to supply the general grid. So a parallel connection of source, as we've already evaluated and confirmed, means that the current values should add together. And we've looked at that with our multi-winding transformers. And so what we're going to do is the same thing, but with two separate transformers. So in this example here, we have 100 volts worth of potential for a load, and 10 amps maximum is what we would be able to provide. And it's simply taking those two current values and adding them together. So what do we need to consider when we connect transformers in parallel? Well, the first thing would be we need to maintain proper polarity between the transformers. So that means even terminals connect together and odd terminals connect together, just like what we did in the multi-winding transformers. The transformers need to have the same primary and secondary voltage ratings. And the transformers need to have the same percent IZ rating, which is something we're going to take a look at in a presentation in the future. Interestingly, at the bottom here, it states transformer kVA ratings do not have to be equal, and the transformers do not all have to be additive or subtractive wound. So this is how a typical connection would look for parallel transformers. I've got bus bars, because that's typically how we're going to see this type of arrangement conducted. 2400 volt primary, 240 volt secondary. Notice H1 connects to the same bus bar for all the primaries. H2 connects to the same bus bar. And then on the secondary, X2 connects to the same bus bar, and X1 to the same bus bar. So they're maintaining proper polarity. Now, what if you were running into a situation where you had different combinations of transformers? So on the far left, this is two additive polarity transformers, same as what our previous diagram was. This is two subtractive polarity transformers. So the only difference is the orientation of where the terminals are located, but you'll notice that X1 still connects to the same bus bar. And then what if we had a subtractive and an additive polarity transformer? Somewhat uncommon, but I suppose it could still happen. Just because they're not both additive doesn't mean you can't use them together. So X1s connect to the same bus bar, X2s connect to the same bus bar. Regardless of the transformer winding type, even number terminals connect together and odd number terminals connect together. What about different kVA sizes? Well, this one here, 210 kVA would give me a total of 20 kVA load capacity. A 10 and a 5 would give me 15 kVA load capacity. And a 10 and a 100 would give me 110 kVA load capacity. So they do not have to be the same kVA rating. So there's some things that we need to consider when we do a parallel connection of transformers. One of them is a confirmation test prior to the final connection that would prevent a hazard from taking place. And the second one is to consider the implications of transformer backfeeding. So the first thing we're going to look at is a transformer closure voltage test. This is used in single-phase and three-phase systems. And really what we're trying to do is a confirmatory measurement to ensure that we have connected the transformers correctly. And we're doing this confirmation measurement prior to the final connection. So notice here, there's my jumper wire to connect these two sources in parallel. The jumper wire has not yet been completely connected to this second source. And what we're doing is we're taking a voltage measurement between the two. And what we should read is 0 volts, and in this case, DC. But in the real world, you're looking at something under 5 volts. There's always going to be a fluctuating or a floating voltage that we're going to see between two energized items. So expecting a flat line of 0 is kind of unrealistic. Now the voltage across that final connection should be extremely low. And if it's not, what would result if the difference between them was not high enough to cause damage, it would cause circulating currents between the two sources and overheating. So long-term damage could result. If, however, the voltage difference between these 2 points was very high, like a couple hundred volts, when you do make that final connection, you could create a short circuit, possible arc flash, and of course, destruction of the equipment and injury to personnel. So, on our connection here, I've got 2 transformers and 2400 volt bus system. It's energized, and what we do is we make all the connections, and then this one here, the final connection, before I connect it into the second transformer, I energize everything, and then I take a voltage measurement between these 2 points. If the voltage comes out at something very, very low, I know that I can do that final connection and it should be okay. So we would then de-energize the connection up here. We would complete the final connection, and then we could confidently throw the switch and turn everything on, and it should be okay. Now, something to consider is that when transformers are connected in parallel, they require disconnects. They require disconnects to isolate them for maintenance or replacement purposes. If only the primary disconnect is opened, individuals can mistakenly assume the terminals are de-energized. And so often you'll get disconnects on the secondary as well, but the primary is really what the absolute minimum standard is. And you will always have to have disconnects on the primary of any transformer installation. So let's see what this hazard is that they're referring to. So on the left here, we've got two transformers operating in parallel, and they are both stepping down voltage from 12 kV to 480 volts and supplying an equal amount or equal to their rating of 480 volt load on the secondary bus system. Now, one of the transformers we are going to open the disconnect on because we need to do some preventative maintenance, or we're simply going to remove it and replace it with another one, who knows. So here's the second one, transformer 2 is still stepping down 12 kV to 480 and supplying that bus. But look what's now happened to transformer 1. Transformer 1 is now stepping up 480 volts because the secondary is energized now and the primary is not. And it is energizing the primary at 12 kV. So it's stepping up the voltage from 480 to 12 kV. And so this introduces some odd circumstances. We don't see it in a whole lot of places in the electrical industry, but this is one of them. So if you were to take your multimeter and measure the line side of the disconnect, you would read 12,000 volts AC, and you would expect that because it's connected to the primary bus. On the secondary side, you would also register 12,000 volts. And so that's something to be aware of. Just because you've opened the disconnect doesn't mean that anything is de-energized. The problem comes if someone tries to measure across the disconnect. So remember, the line side is 12,000 volts and the load side is 12,000 volts. What happens when I try to measure across the disconnect, like this? I'm putting my voltmeter across it right now. What voltage am I going to measure? And this is where the hazard takes place. Your voltmeter is going to measure 0 potential difference. And people who are unaware as to where and how to measure across disconnects properly may mistaken this as a safe reading and therefore a de-energized system. So you always have to be aware not only of what the voltages are, but where are you measuring? What makes sense? And can you extrapolate that to determine if you are at risk of any hazard? So I hope you've enjoyed this presentation. We still have another couple remaining in order to fully illustrate how transformers are utilized within the electrical industry.